to structure analysis and design 2. We are working on the wind loading. Last week we have performed the calculation on design wind speed. We design theta. We have calculated 4 design speed on the orthogonal directions. Now this week we are working on transferring this design wind speed to the pressures. We will see how the pressures will be calculated for those design wind speed for our examples, and probably the UDL load from that design wind speed. So that's the final answers for that. We also perform one examples in the lectures where we have calculated the design pressures. Now today I will continue on the examples which we have done last week. Let me share the screen. And some notes before we start. If I go too fast and if you have any questions, there is no offense to stop me and ask me the questions. Okay, it's not it's always have a good healthy discussions while we are working. Ask questions so I can stop, put more details, because I'm not sure what is happening on the other end, and when I start talking on the screens, and after 1 hour I get exhausted and I just quickly want to go through it and finish the one. But you can stop me anytime. As I mentioned, there is no any big issue for me that if you can stop me and ask me any questions, I can go back and add more details as you need it. Now we work on these examples. As you can see that that the industry buildings is to be built in a rural setting of an outskirt of Canberra, determining the wind force for the strength limited on the roof and wall of typical interior frame. So interior frame is given to you here. Typical interior frame. The roof has a pitch of 7.5, so that is the roof 7.5 degree. By the way, the Australian standards recognize that 7.5 pitch is considered as a low. I think it's not high side, so you will have this low. So you have two options. You can have alpha equal to 10 degree, that is considered as a low, or you can have a alpha greater than less than 10 degree, and you have alpha greater than 10 degree. Based on that, they have, I will show you where. So 7.5 is falls in this category, alpha less than 10, which is kind of low pitch. I will explain you that in the figures. So just quick notes when I read this 7.5. I just found. So frame has a center to center distance of 6 meters. So from this end to this end is a 6 meters. From here to here 6 meters. Here to here is 6 meters, and so on. Height is 5 meters. Height is 5 meters. The door for the buildings are shown, and there is a fixed roof vent, 130 millimeter airways. I think you know the story. There was a 130 millimeters width of airways in the halfway through of the length, and consider two cases where all opening except the roof vent are closed. So we need to consider two cases, that everything is closed. Case number 1, everything is closed, meaning this door is fully packed closed, this one closed, this one closed, and see what is the, because look, the opening and closing of the door only affect the internal pressures, right? It will not affect the external pressures. The external pressure does not depend on opening and closing. The internal pressures, that's building will inflate or deflate, or positive pressure or negative pressure. So you can say pressure or suction internal, depending on which side of the door and windows are open. So we need to have all opening except this one are closed, and critical opening are open. So we need to identify which one is critical opening. They did not say which one is critical opening, but you might say, okay, this is critical opening, we can work it out that, okay, this is case number 1. Then we close this one, we open this one, and then we work it out, what is the effect internally. Then you close this one, we open this one, and so on. So there are various options available. You can have a multiple options combinations, but by doing the practice as an engineer, by working out for many, you might develop the skills which one getting the worst. But for our case, I will demonstrate that one. So you need to feel how does it I'll work it out. Okay, so I hope you got an idea that you know the story here, V side beta and VR, MZ care. I don't need to take you through all these story again. We find 8 different cardinal direction, then you have MZ care and this MS, MT, V side beta, then you find side with asset, design wind speed and all. Then you just calculate this. You first calculate 8. From 8 you get the 4, right? Based on these orthogonal directions. You remember these big figures that we use to get from 8 to 4, right? Because you have 8, regardless of your orientation of the buildings, you will get these 8 different speeds with the red one, right? Regardless of where it's going to, so where the buildings will be located, the red one is just coming everywhere. It's just a direction, the wind coming from 8 different directions. That is a red one. It's not depending on which side your building is oriented. It's going this way or straight or going this side or and so on. So there is no any relationship on that one. You have 8 speeds coming on here, and then after 8 speeds we find out how the orientation of the buildings works out, and then we end up finding the plus or minus 45 degree, and we take that zone of plus or minus 45 degree and we find the maximum speed on that 0 degree, 90 degree, 270 and so on. So then you find those 4 speed that you end up with using here. So there are 4 speed that we're going to work. So now we, whatever you done previously, that's okay, but now we're going to make sure that we use this 4 speed and we work it out this okay. Now let's let me get my solution up. So I have on the track. Okay, so now we have only one equation that we're going to help the pressures. Where is that equations? The magical equations that let me open that one and let me turn off my camera. Let's open this and the magical equations. Where are you? Here you go. Okay, so that is the equations to calculate the pressure. So on clause number 2.4.1, that's the equations that we're going to use. So let me copy that equation first. Let me copy that equation first. So the pressure equations, pressure P equal to 0.5 rho R V design theta square C fig C dynamic, right? And the unit is pascals, by the way. The unit is Pascal. So you have these equations 0.5 rho R V design theta square C fig C dynamics. Always C dynamics taken one. As I mentioned, we are not considering the dynamic nature of your structures, because as you know, this dynamic means that within 1 second it will just bounce back. Okay, it's very short periods. We don't have this one. So always we take this C dynamic one in our course. You don't need to work it out. There is a special branch where engineers need to work out this C dynamic. This is not this. There is a specialization to require to perform this C dynamic analysis. So we are not sensitive. Our structure is not sensitive over C dynamics, so we take it 1. In this case, we have 0.5 density of the air 1.2 kilogram per meter cube. Don't change the units. And where is coming from? That is coming from here. Density of air 1.2 kilogram per meter cube. Okay, don't change your newtons or anything. And V design speed, we have 4 different design wind speed. Let's say work it out. This first one 33.8 square, and C fig and C dynamic is 1 and the unit is pascals. So if I want to work it out this one, that let's say this is the direction of our structures. You know that this is about 15 degree from the north, that is given in our examples. So this is theta equal to 0 directions. For that we have a pressure. We have a pressures equal to 0.5 times 1.2 times 33.8, you get 20.28 pascals. And if I divide by 1000 to get it in the kilopascals, so divide by 1000, and so you will get let me check 0.5 times 1.2 times 33.8 square. You get 685. Sorry, I screwed up. You get 685.5 pascals. And if you just divide by thousands, you get 0.69 kilopascals, right? So the pressures going in these directions would be 0.69, and don't forget the CIV kilopascals, right? I hope you understand that pressures on the theta equal to 0 directions, theta equal to 90 directions. The pressures that you will get is 0.5, 1.2, and we change this one to 34.5. So let's put 34.5 square. So 0.5 times 1.2 times 34.5 square, you get 714 pascals. Divide by 1000, you get 0.71 kilopascals. So here you get 0.71 kilopascals. By the way, we're going to check it. Okay, pascals. Let me write it down here. Theta equal to 0. You have pressure about 6. Oops, sorry, what happens here? You have a 689 pascals. CIV pascals. Sorry, CIV pascals. When you have a theta equal to 90 degree, your pressure would be around 740 CIV pascals. Okay, then you come here, theta equal to 180 degree, pressure equal to, let's say theta equal to 180 degree, pressure equal to, we put it 40 now. So 0.5 times 1.2 times 40 square, you get 960 CIV pascals. Let me put in the bracket, so that is pascals unit. So you have a about 0.96 CIV, and then you have a here theta equal to 270 pascals equal to 41.4. So you have 41.4, theta equal to 270 equal to 41.4. So 0.5 times 1.2 times 41.4 square, you get 1028 CIV in pascals. So I think 1.03, you can take it 1.03 CIV in pascals. So I hope you understand this, that we converted the velocity into pressures with the CIV. I know CIV, we need to work it out. Now I have to give you one important notes here. The important notes here saying that I have here. Look, when you stop here, okay? You stop here and check it. What check you need to make it? That okay, when you get the pressures 50 CIV C dynamic, don't worry about C dynamic. If this number is 50, it's very low, because as I mentioned, you have this 0.5 times 1.2 times by 30. Where is 30 coming from? Because you, regardless of your structures, you cannot use less than 30. This one, this is given in the standards. I can show you again that this one never be less than 30, regardless of that. That is 30 written here. So for that case, if I at least put 30, you have 540. So 50 is too low, right? Your velocity would be less than. So you're something wrong. Go back and check it. Around thousands, yes, it's okay, right? If it is thousands, meaning that you have 540, so up to 540 to thousands, it looks okay. If it is 1500 to 50,000, there is something wrong, very high speed. So please keep a note that this answer is not a practice, but these answers should play between 500 to 1000, right? something like that. You can't just make it this 50 or so on. So that is the pascals that I want to put it in the notes here, that okay, these all the values looks good. Okay, it's not, what can I say, it's not a rules, but it's just with a lot of practice we can make it that okay, we should have some value in that range. Any questions so far? About that, you have buildings. Okay, so if you don't have any buildings, then you have this north, south, east, west, northeast, southeast, southwest, and northwest. Do you understand this? Okay, forget the building. There is buildings, doesn't matter. We have Canberra and we have 8 direction in Canberra. Okay, standard saying that for our maths purpose, for mathematics, you know what do you mean by mathematics? We need some numbers. We can't just say that north, south, and this is. We are engineers. We are not north south guy. We need the numbers. We always play with numbers, right? So the standard said okay. Let's do the some numbers. So let's say you take beta equal to 0 degree towards the north, and you get 45 degree every time you increase, right? So you say beta equal to 45 degree, and beta equal to 90, and so on. You got so far? Building at the moment. This is just the beta that will just give you the numbers. And now we will just say that okay, there is some wind coming from here, wind coming from here, wind coming from here, wind coming from. There is no building at the moment. I just figure it out. If I have some field here, what would be the wind in the 8 different directions is coming? Okay, there is no building at the moment. Okay, you got it? Okay, now so standard said beta equal to 0. Okay, now they say that okay, let's put the building. Now, when you put the building, building has its own axis. You got my point? Building, whatever the structures you have, you draw the parallel line along this big line and draw parallel line along these lines. You happy to draw these orthogonal lines? That makes sense. Okay. So when you draw it, regardless, don't look at this north south and all. Okay. Don't look at north south. And don't look at this north south and all. We just look at the buildings. Okay. And forget that you have north, south, and east, west. Okay. Okay. So far, so good. So the standard says that okay, when you have a buildings like this, and theta, take theta equal to 0 here. Okay. Take theta equal to 90 here, and then theta equal to 180 here, and theta equal to 270 here. Okay. Now this theta represent the axis of your structures, orthogonal axis. You got it? And if someone said, what about if I have a structure like this? Then you just move here, so that theta comes here. So still you can rotate like this, right? You see what I mean? Yes. So you have two different angles. One is for 8 cardinal direction. Another one, theta, is representing your building axis, the orientation of the building axis. And if someone sitting north buildings, then your beta equal to 0 and theta equal to 270 sitting together. Beta equal to theta equal to 0 and beta equal to 90, something like that. So they will be spot on each others. That is always theta equal to 0. Based on, it's not saying based on this, because everyone on the same page, every engineers on the same page, it says that theta, take theta equal to 0 here. Someone said if I have orient this one, still you orient this one this side. If someone said if I have angle like this, still it will comes like this. You see what I mean? We have taken the 4 different pressures now. Now we need to make a look. We need to do the workout one by one. Okay, one by one means we just need to work it out one by one, because we have. So when theta equal to 0 degree, which is here, you have pressure is 0.69 CIV kilopascals. When theta equal to 90 degree, you have pressure equal to 0.71 CIV kilopascals. When theta equal to 180 degree, pressure equal to 0.96 CFIC kilopascals, and theta equal to 270 degree. We have pressure equal to 1.03 CFIX. Now we need to take it one by one. In the ideal world, we take theta equal to 0. Let's say wind coming from here. All right, so that's hopefully you can see the screen. So we in the ideal world, we will take this case and we will find out the external pressure, internal pressures. Then we take theta equal to 19. We find out external pressure, internal pressures. Then we go theta equal to 180 and theta equal to 270. But by looking at the structures, it's a symmetric structure. Symmetric structures meaning that if you look at the structures here, then if you draw the line here, then this door D1 and D2, you have two doors as well, right? Someone might say, oh, door size is not same. What you're talking about the symmetricity and all? Look, when the winds blows from here or here, and if you keep the door open, you will see this tiny door or the smaller one, it will not affect too much, right? So I would say that we have a symmetry. Symmetry meaning that you have theta equal to 0 and theta equal to 180 degree. You have a symmetry between that one. So we can make a decision here that between theta equal to 0 and theta equal to 180, which one create the worst case for our structures? Because if you work out if the structures can stand in the worst pressures, it can stand in the low pressure. So between these two, theta equal to 0 and theta equal to 96 and 69, I would say that if I design my structures theta equal to 180 degree with the pressure of 0.96 CFIG, I would say I don't need to do theta equal to 0, because of course theta equal to 0 will have a lower pressure created on our structures. So I would say that if I design my structure for theta equal to 180, the structures would be standing for theta equal to 0 direction as well. So for that case, I can say that theta equal to 0 is not required at this stage. If you want, you can do it. It is not required, but to start with, we can start here theta equal to 180, and we can say that theta equal to 0 as a 0.69. So let's make a theta equal to 0, because this is the critical, this is the worst case. So for theta equal to 0, we have to calculate two pressures meaning external pressures is equal to 0.96 CFIG. Let me take the symbols and I will show you that symbols as well. CFIG E, and internal pressures is equal to 0.96 CFIG I, right? So I can make this equation into two equations saying that external pressures and internal pressures by changing CFIG E and CFIG I. All right, now let's work out the external pressure first. Let's work out external pressure. By the way, when you have a structures, your external pressures will be different on all the different walls depending on where it is hitting. Internal pressures, they are same. Okay. So let's work out the external pressures PE first using that equation. So for that, we need to calculate CFIG E, where I can get the equation for CFIG E, and CFIG is telling the aerodynamic shape factors, and aerodynamic shape factors is looking it at here, CPE, KA, KCE, KL, KP, right? So that's the equations I'm getting it down here. So CPE, KA, KCE, KL. If any problem, just unmute yourself. Okay. Sometimes when I'm writing it, I don't know whether if you are typing, I might miss your question. So it is good that just say hello, check the chat. Someone has put some questions there. Thank you for that help. All right. Now this CPE that we need to work it out for ourselves. Now let's say you want to work out this. Let's do the CPE at the end, and then rest we're going to do it CPE1. Okay, so let's work out CPE first. CPE. Now let me draw the structures. Now CPE has because look, we are drawing this one. Okay, what happens here? That I think I should get these figures down there because we're going to use it. Copy close to our calculation. So let's paste it. Okay, so here we have this building. So now the wind is coming from here. Okay, forget all the directions, but wind is coming from here. So this is my windward wall. This one I draw it up. Okay, so this red one, which I draw it up here. All right, so that's good. Red one I draw. Now this one here. This is my windward wall. This is leeward wall. And this one is roof and roof. They call this roof up, I think upwind, or I can tell you where the word is, up slope or something. Let me find out that roof, downwind slope. Okay, here you go. They talk about this downwind slope on table 5.3, downwind slope and upwind slope. That's what they classify the roof. So upwind slope roof and downwind slope roof. In that direction will change. The wind is coming from here, theta equal to 180 degree, or you can say that theta is coming because this wind is coming from here, right? Now, and if the wind is coming from here, this direction will change where the windward and leeward. Now, when the wind coming here, and then for that CPE value for our case, look, CPE values is the complicated one, external pressure coefficient. External pressure coefficient, that's the name of CPE. For that CPE, you have a total 6 CPE or total 6 tables that you need to deal with. If someone say that I want to calculate the CPE, you have a 6 tables, total 6 tables. Now I will tell you what is the 6 tables is. Table 5.2a is for windward wall. Okay. Table 5.2b is a leeward wall and 5.2c is side wall. So basically 5.2 is dedicated for walls, windward wall, leeward wall and side wall. So you have 3 tables, that is a windward wall and side wall. There are another 3 tables which is dedicated by 5, which is represented by 5.3, 5.3b and 5.3c is for roof. Okay, I will tell you how you can distinguish between these 3 tables. So it's clear. If someone said calculate the CPE for me, you have total 6 tables to deal with. 6 tables for different, 3 tables for wall and 3 tables for roof. Let's start with windward wall. Now the windward wall is saying that for our case, our height is less than 25 because I think you have 5.25 height. So we have less than 25 and Z equal to H. So you have 0.7 positive value. It says that what is positive value? It says that you always get this. Let me put this red one, that you have these pressures with the positive 0.7 CPE value, always positive. When the wind blows on this side, when the wind coming from here, you have this positive, you have push natures. That's easy. There is no problem. Windward wall, you don't have any issue for calculate walls coming from here, from the table number 5.2a windward wall. And please keep in mind that you have this 0.7 most of the time in our course. If you don't use these tables, keep in mind CPE is 0.7, right? Because you have 0.8 and 0.8 is does not applicable. This is for tall buildings and normal structures. We take it 0.8, but our wind does not vary with height, so we always take it 0.7. So if someone say that what is the CPE value for windward wall, 0.7, okay, for our course. So that's 0.7, quite easy. Now if you turn the page over, next page, and then you will see 5.2b and CPE value is leeward wall. So we can go on that side. So let me go back and do the CPE value for leeward wall. And we have a couple of things to do here. Now we have this theta, wind directions, and see figure number 2.2. So we have theta equal to 0 and theta equal to 90. So figure 2.2. Figure 2.2, where is it? Theta equal to 0 here. Theta equal to 0. Either wind is coming from here or wind is coming from here. Right? We are in our case theta equal to 0 because wind is coming from here. You might say theta equal to 180. What are you talking about? Because 0 and 180 they are considered as a one axis. So theta equal to 0 or theta equal to 180. They would say theta equal to 180. Right? So in our case we can take theta equal to 0. Right? You agree with me that wind direction theta equal to 0 because you can see theta equal to 0. Wind is coming from here, by the way, in our case 180, but is on this axis theta equal to 0. So we have theta equal to 0. Now roof type. How do you gonna discuss this roof type? So if you come back on these figures, so this kind of like a slant one, you have a gabled roof, right? You have this slope and gabled roof. This is also gabled roof, and then you have this you have this hip roof where you have these 4 different slopes, right? So that is the hip roof that you have it on here. So I hope you understand the gable roof and hip roof. The gable roof, we have a gable roof, right? We have this gable roof in our case. So let's do the gable roof. Sorry, yes, we have gable roof. So I hope you understand hip or gable. We don't have gable roof, and we have theta equal to 0. That's one. Now roof pitch alpha should be less than 10. Basically, this saying that you have a low roof pitch. Like if I take it here, you might have a alpha equal to greater than 0 or alpha is less than 0. Okay, so basically it says that okay, you have this kind of roof like a flat, or you have this kind of roof. Okay, so we have this kind of flat roof. Alpha is less than 10 because alpha is 7.5 in our example. So we have alpha equal to 7.5. So in our example, alpha is given. Alpha is 7.5. So this is all good. Alpha is 7.5. So we are in this row. Now we have this category D and B. Okay, let's work it out, D and B. So how do you gonna work it out, D and B? We use these figures again. And please note how we're going to work it out. D and B is here. Please pay attention here. So that when the wind is coming, by the way, I'm talking about figure 5.2. When the wind is coming and hit this first edge, perpendicular one is your B, and this parallel one is your D. I hope you understand. Wind is coming from this way. This is B, this D. Similarly, if wind is coming here, always this one B, this parallel is D. Hope you understand that. Wind is coming from here, this is B, this is D. Wind is coming from here, B and D. So always this perpendicular when the edge face the wind is B. Edge that parallel that just slide the wind across to this edge is your D. I hope you understand that. So wind is coming from here, is hit this edge, so that is my B, and it's go across this way, that is my D. So in that case, B equal to 24 meter, D equal to 16 meters. Now this will change if the wind coming from this side. That become your B and that become your D. I hope you understand that. So in our case, B equal to 24, D equal to 16. So let me take the ratio. B equal to 24 and B equal to 24 and D equal to 16 meters. So what we need to do it, we need to take the ratio, I think. We will take the ratio D on B. Okay, let's take the ratio D on B equal to 16 meters over 24 meters. So 16 on 24, you get 0.7. So 0.7 is less than 1 on the table. 0.7 is less than 1, and this is the minus 0.5 is just pulling out. Minus is pulling it out. It's not pushing. So you have this, and this is suction. That is minus 0.5. right? And if you don't know these directions, you don't need to remember. You can come back to this page. You don't need to remember that direction again. If you come back on this page, you will see when the external pressures sign positive when it's push, right? So you take positive, and external pressures when you have negative value, you put the arrow coming out, not going in. Okay, so therefore we have external pressure positive, negative. So I hope you understand that. All right, so you work it out these two external pressure coefficient. I hope you don't have any questions to work it out. I hope everyone now in the positions to use table 5.2a for windward wall. And if someone asks you to find the CPE value for leeward wall for any directions, you have a you have this. You have these tables, so you can able to classify whether theta equal to 0 or theta equal to 19. You can classify hip roof or cable roof. You can classify what is alpha. Basically alpha is this one. Alpha is this, and that is given say 1.5. so I hope you know how to do this alpha as well now, and D on B I already explained, and then based on that you can get the CPE value. Now roof. Roof is little bit side wall does not comes in here, because you can see these side walls. If I hit this one, the side walls is not that critical here. We just need to work it out this, because when the wind hits, it will go. But if you want to work it out side walls, we can work it out. That is not an issue. We can draw the plan view and we can work it out the side wall as well. For your completeness, you might work it out the side wall as well. Now for roof, we have 3 tables as I mentioned, and we need to make it 3 tables: 5.3a, 5.3b, and 5.cc. So I can explain you how you're going to see where is a. So the first table and second tables is basically talk about alpha is less than 10 is a low slope, and alpha is greater than 10, that is the high slope. So basically it says that whether your roof is like this when alpha is very big, greater than 10, or you have a roof like this. Sorry, you cannot see here. Or you have a roof like this, flat one, where your wind just go and slide off, or you have this slab. So that's one. What is this one? Oh, alpha is greater than 10. Again, this is stiff roof. And what is the difference? External pressure coefficient for rectangular enclosed building, downward slope, and for hip roof. So if you are talking about downward slope and alpha greater than 0, you can use this one. And this is up. So between this and 2, these are used for alpha greater than 10. So these 2 tables can be used alpha greater than 10, like this one, and it's talking about whether you want to down when the wind coming here, whether you want to calculate up or you want to calculate down. So that is, they have given you 2 table for alpha greater than 10 with the up and down. Okay. In our case, we have alpha less than 10, so we ignore these 2 tables. We're going to come here. I hope you understand that. Unmute yourself if you have questions there. So let's continue with our one. So I think we classify that we're going to use this this roof. So we're going to classify this roof alpha less than 10, and we have a crosswind slope. I think the crosswind is meaning that this is a crosswind and this is the longitudinal wind. So like this is cross and this is longitudinal wind. So that's what the meaning of crosswind. We have a alpha less than 10. That's all good. So we need to have a different value for H on D less than 0.5 and H on D greater than 0.5. Let's work it out. H on D ratio. So you have H on D. So H we calculated, I think, previously, which is 5 point something, I believe. There you go, 5.5 meters. So if I have 5.5 meters height and then depth 5.5 over 16, so you will get 5.5 over 16, you get 0.3, which is false in this category, which falls in this H on D less than 0.5, which is because you have 0.3. So we will need to use these columns. Now it says that we need to have a H on D ratio from 0 to 0.5, 1, you have the same value. From 1 to 2H, you have 0.5 to 0 and 2H. Basically, it says that when you hit the first one, you will have higher pull natures, and then when yes, the wind is going across, you will have smaller values. So let me put that details here. So it says that, okay, you have negative, and from here to up to here, you have up to, meaning that you have a pressure going on this one. You have two values, minus 0.9, minus 0.4, and that measures from here to here, which is 1H. This is 0, and then you go across, and 1H means 1 times 5.5 equal to 5.5 meters, right? Where is coming from? Here. So it's measure from the windward edge, from the roof, and 0 to 0.5, 0.5 to 1, you have same values. And then from 1H to 2H, minus 0.5 and 0. So from 1H to 2H, so it's 5.5 times 5, so you have another 5.5 meters. So that is 11 meters, by the way. And you have little bit smaller, continue, and this is taking about minus 0.5, 0. And then when you exit, the remaining one is here to here. By the way, this is how much? We have 16. So we have 11, so remaining 5 meters is 16 meters. So you have a remaining one is going here, and it's telling me minus 0.3, 0.1. These all the values I taken from here. So this is minus 0.9, minus 0.4, minus 0.5, minus 0.3. Basically, it says that when they hit the enter, this is the guys who gonna hit hardest. So you have very high up lifting pressures, and then when it's exit, it has low. Okay, so I hope you understand how you're gonna calculate the CPE value for three different. And why is minus 0.9 and minus 0.5 two different values? You might think that, okay, when the wind hits, where is my when the wind hits the roof, will do this like this, minus 0.9, minus 0.5. So it does not just stay the roof strong. You will see they will shake, so it will have waves. So therefore it's considered two different value, and which one to select is depend when you combine with external pressures, right? When you combine with external pressures, you will consider one of these value would create the worst case scenario, then you pick that one. So we calculate this CPE value right now. Now Ka, what is Ka? Let's work it out. Now Ka, where it is? So for windward wall and leeward wall, we don't need to worry about Ka, because it's just consider your roof and side walls. As I mentioned, only the roof and side wall has a high area, where the standard wants you to reduce the pressures if you have high area. Like if you can think of the pressure is hitting on the very high area, the pressure would not have that strong intensity as you hit by in the smaller area. So standard allow you to reduce that one for side walls and for roof. So let's say for our roof, let's say for our side walls, what is the side walls area? So you can calculate this side walls area. Probably you can calculate this area of the side wall, let's say 16 meters, 16 meters and 5 meters and so on. You can calculate that. But let's say for side walls is not a critical for us. So let's say Ka equal to 1 for side walls. Now for roof, you can see they have very large, significantly large area for the roofs, right? It's not a small area for the roof. So let's say for roof we have 6 meters of these frames, and you have 16 meters. So you have 6 meters, 6 meters. So tributary area, you would consider that you have a, let's say this is the tributary area, 3 meters on each side. So you will have a 6 meters by 16 meters of area, which is considered as a 96 meters square. So if you come back here and 96 meters square, and it's about 100, you might say, oh, 9600 is not correct, but then you can do interpolation, is going to be very close to the 0.8. So let's say Ka value for roof is 0.8, right? So I hope you understand. And for leeward wall and windward wall, we don't need to consider the Ka value based on these tables. Now Kc. Now Kc. Kc is a combination factors. One table is given for you to consider the Kc values. Now there is a one catch. Keep in mind that Ka and Kc, when you multiply, you will need to be less than 0.8. You can't just, basically standard says that if you take Ka equal to 0.8, don't take Kc equal to 0.8 as well, because you have 0.8 and 0.9, right? So the standards wants you to just use one of each, right? And basically I explain you this KCE. KCE is a combined factors. When your wind hit onto the surface, you will not have worst case for everything. You can read. So all the winds calculated are worst case, and it is not always possible for the worst to occur on every surface at once. So if the wind hits on the windward wall, your side walls, roof and all are not worst case, only windward wall is worst case. So you can combine and reduce that pressures. But catch here, you can't increase that value so fast. So let's say, as you know, we will take one, because we already take into account this Ka equal to 0.8. So let's take a Kc equal to 1, because as I mentioned, these are stopping us to consider this Kc. You can consider Kc if you have this one for all cases. So let's say Kc value equal to 1, because standard wants to have a Ka times Kc not should be less than 0.8. So should not be less, should be greater than 0.8. So if you already consider this 0.8, we can't go for Kc 1. So that Kc is 1 for everything. Alright, so now KL is a local pressure factors for cladding, only applicable for the external pressure. So that sounds good. No, sorry, I'm not showing you this one. So the KL is local pressure factor for cladding. Local pressure shall be taken cases except this one. So it's basically saying that when you have a very small area, like a window, do you remember that stained glass window in our church examples? They have nice figures here. So if you don't want to calculate the pressure on the whole surface, but very tiny surface area that you want to say, and someone might say, how do you gonna figure it out whether it's tiny or not? There is a condition here. If you check our lectures, we have explained you how you do it, this tile area, and here we are considering the whole structure, the big structure. So KL is not applicable. Like if you want to just specifically concentrate on particular region, small region, then you take this KL equal to some factors, but we are taking 1 because they are taking this local pressure factor does not apply. Permeability Kp. Kp is permeable cladding reduction factor for roof and sidewall. Again, this is just apply for roof and sidewall, does not apply to windward wall and this one. And probably we don't have anything that account for reduction in external pressure due to the permeability, and there is no any such permeability or anything, only applicable to the element of slide wall and roof. Apply when consist of permeable cladding and open area are relatively small, up to 0.1% to the 1% of your opening area. So I think we don't have those things. We have take the Kp equal to 1. Kp equal to 1. So now we good to go to calculate the external pressures for our all the walls. So let's calculate the external pressures of the walls. Now the KL, that's permeable cladding reduction factor, shall be taken 1 except where an external surface consists of permeable cladding and open area ratio is greater than 0.1 or less than 1, and value given in table 5 may be used for negative pressures. The open area ratio is the ratio of open area of the surface to the total area of the surface. Figure 5 shows the dimension of dA. Is the local pressure factors. When you want to calculate the pressure on the small area, not the whole structures or the whole wall, but any particular small area like a window or door that you want to calculate, you consider the KL. And that's the condition here. Area is less than 0.25 a square, and the a value you can calculate the minimum of 0.2b, 0.2d, and h. We have taken the examples where you consider the KL. Like in the lectures, we have KL value as 1.5. So it's basically saying that when you have a small area, your pressure increase, right? You increase by 50%. You can think of the pressure coming onto the, where is my pressure coming onto the small area. You will hit the wind, and on that small area your pressure is very high compared to the very large area. Now here we are only considering the large area. We are not asking to calculate the pressure on the small portion of the structure. So we are taking KL equal to 1. Does it answer your questions? All these calculated. So let's jump onto it. Meaning that we will have this pressure 0.96 times by CPE, KA, KCE, and we have all this value. Remember that KP. Right, now let's calculate, let's draw the figures. Let's draw up the figures. So I think you know what I'm talking about. Sorry about my unsymmetric, but I hope you know what I'm talking about. So we will have a, let's say, what was that? Red one is the push, and blue one is the pull. So, oh sorry, red one windward wall. This wind is coming from this side. We have windward wall. Now for this case, we have pressure 0.96. Where is coming from? Because we have 0.96. We have 0.96, and then we multiply all this. CPE for windward wall is 0.7, right? So let's say CPE for windward load 0.7. Then we have everything one for windward wall. You can just say KA, KC, KL, KP. All these, how many 4 Ks there? 1, 2, 3, 4 Ks is 1 for windward wall. So that is 1. So I hope you understand that. And then times by, we will have a portal frame 6 meters. So this is a pressures. By the way, this is pressures. So if I want to calculate the pressures, 0.96 times 0.7. So you have 0.67 kilopascals pressure coming onto the wind wall. Now we want to calculate the UDL load. If I want to calculate the UDL load coming onto that wall, so you multiply by this 6 meters, right? Because that pressure is coming here, and this would have a tributary. The distance that you will take it for UDL load is this 6 meters. So you multiply by 6 meters because this is kilonewton per meter square. So pressure time perpendicular distance, you remember that from our examples. So 0.67 times 6, you get 4.0 kilonewton per meters as a UDL load. Here you get 4.0 kilonewton per meters. I hope you understand that. Now we have a pressure. I'm not putting negative or positive. I'm just going to put the arrows. Now this one we have to have a minus 0.5. So everything is same. Everything is same here. We have minus 0.5 here. So pressure equal to 0.96 minus. I'm not putting minus, but just the arrow will tell me that is minus. So 0.5. All the factors are 1, and then you have 6 meters. So if you work it out, you get 0.96 times 0.5 times 6, you get 2.9 kilonewton per meters. So you have 2.9 kilonewton per meters. Right, so let me cancel that. And now we will have another one, roof. Let's consider these first numbers for our case, that you have this first number minus 0.9. So let's say you have minus 0.9 up to here. So if I plug the minus 0.9 here, which is 0.96 times 0.9, I'm not putting minus, the arrow will tell me minus 0.9. And please note, we have a 0.8 Ka for roof. So you just need to multiply 0.8. Let me show you that one. Pressure equal to 0.96, and then you have 0.9 as a CPE, and then you have a 0.8 as a Ka, and then you have 6 meters. So I hope you understand that. So 0.96 times 0.9 times 0.86, you have 4.1 kilonewton per meters. And then you go here, you have a first number is minus 0.5 and you have a roof. So let's say if you substitute that minus 0.5, you get 2.3 kilonewton per meter, right? It's just here you put instead of 0.9 you put 0.5, you will get this 2.3, and then you will have a minus 0.3. I'm just taking the first number, so minus 0.3. So you will have minus, meaning it's going this way. So just substitute 0.3 here, you will get 1.4, and I'm not putting minus because the arrow will tell me whether it's minus or plus. Okay, so that's all UDL load coming onto that portal frame. And the second case, let me draw it up. This will same because it does not change, only the roof change. So it is 4 kilonewton per meter, and you have 2.9 kilonewton per meter for leeward wall. And for roof it's changed because you have these second values, that minus 0.4, 0 and 0.1. So you have minus 0.4. So if you substitute just minus just 0.4 here, you will get 1.8. And this is 0 in here, and then you have this last bit here, but this arrow going down, right, because it's positive. Because you can see this is 0.1 is positive. So you just substitute 0.1 there, you will get 0.5 kilonewton per meter. So you have two cases for this roof and for this roof, right? Because this is case number 1, where you have this roof is taken 0.9 and so, and there is a case number 2. This is load case, by the way. Load case 1 for external pressure only. Load case 2, and that is just for external pressures only. External pressures, and look, external pressures are vary on the windward wall, leeward wall, and this one. So basically always windward wall pressure is positive. You can see there's a red one. In all other ways you have a negative pressures, and you can see this when the wind hits. And by the way, wind is coming from here. Okay, wind is coming from here, it pushes the wall, all other wall they will pull. Okay, except there is this one, I can put red one, sorry. So red one. All right, so we done those one. Now let's do the internal pressures for this. Basically we just finished this only external pressure for theta equal to 180 degree. Okay, there are a long way to go. All right, so let's talk about the internal pressure, but I hope you understand what is going on. Thank you. Let's continue. Internal pressure, the good news is the internal pressure does not vary on the structures. If you have internal pressures, they will stay, they will be same everywhere, right? So that's the good news. So we need to consider only one internal pressures on all the members of your structures, either wall or roof. Now these internal pressures depend on opening and closing the door, right? How you're going to open the close, and how you're going to how you're going to work it out. So let's say we want to consider the internal pressure or suctions. Let's consider D1 and D2 door are open and other doors are closed. Let's say case where you have D1 and D2 is open and other doors are closed. What is means? So when the wind is coming from, where is my figures? I think I should get that figures. Let me stop this. That is better now. All right, now we have a door D1 and D2 open. So let's keep this one open. When the wind blows, it will just gonna go inside straight away. and all other doors are closed. Okay, so that's what it says. The door on the windward wall is open. So there is a for CPI, because when you calculate the internal pressures, the same equations that you can use for calculating the internal pressures. This one 0.96 C fix I. So internal pressures is equal to 0.96 C fig I, and then C fig I equal to, there is the equation for that. There you go. C fig I is CPI KCI. So that's simple. CPI KCI. Okay, now in that case, let's do this CPI first. Now CPI, we will have two tables only. That is very good. The two tables saying that you don't have variation. So how are you going to classify two tables? When your buildings are impermeables and then you have these closed buildings, no windows and so on, you will use this one. When you have opening, dominant opening, like in our case where you want to think that okay, someone wants to test your structures and they keep the door open on windward wall and the wind is coming from that directions, the straight away the wind will goes inside and just try to inflate the structures. So in that case, we need to calculate this ratio of opening on one surface, that's in our case windward wall, to the sum of total open area on the others walls. So let's continue on that one. So ratio of opening on one wall, that's area we need to calculate. So how much door is opening, and there is an area for that, D1 and D2 door. Oh, there you go, there is an area, doors D1 and D2, D1 and D2 3.6 and 4.4. so that is one door and there are two doors. So door number 1 3.6 meters times by 4 meters, door number 2 3.6 meters times 4 meters. We will add them together. Let me get 3.6 times 4, you get 14.4 meters square area, and then if you add them together you get 28.8 meters square. So area of opening on one surface 28.8 meters square. So that is good, 28.8 meters square divided by, you have an area. You remember there is a vent and they talk about this vent that we keep all the door closed, right? You remember that we keep all the door closed. We have all the door closed except there is a one vent on the halfway through the roof that they talk about these airways 130 millimeters. So that's only we need to consider, and that is halfway through, meaning that is 24 half. So you have 24 divided by 2 times 0.13. 0.13 is basically converting into the meters. So 24 divided by 2 times by 0.13, you get 1.56 meters square. So now let me explain you this. Can you see these structures? Have a opening, let's say wind is coming from here. Okay. And let's say you have opening here 3 meters square. On the roof, let's say you have something, some hole or something or some window, then you have opening here 3 meters square. Okay, so area of opening on one surface. So let's say this one surface where you have opening, that you consider. You got so far on the first one? That okay, so area of opening on one surface. It could be windward wall, it could be side wall, it could be roof, or it could be anyone. So you see, because there is an opening on that one surface. You got it? Now then you forget about that surface or that wall that you have take the opening and check remaining surfaces. Check the remaining surfaces. Don't consider this one. Check the remaining. Let's say you have a window here. Let's say you have window here and you have window here. So you have this window that is open, that's window that is open, that's window open. So you have, let's say 1 plus 1 plus 1 equal to this ratio is 1. You got point? Now in our case, because we need to explain in our examples that in our case we have this doors is open, right? So the area of opening is 3.6 meters times by 4 meters by 2. You got it? This one. Like the one we have here, 3 meters, that is open. This area of opening on the one surface, right? Divided by sum of the total open area, right? So let's say sum of the total opening. This is not open, this is not open, this is not open. Only the opening that we have is that tiny airways on the roof that is given here, right? Now area of that opening is halfway through, 24 divided by 2, because it's just a halfway through, and times by the how much opening, that is 130 millimeters divided by 1000, so you have 0.13 meters, so 0.13, so that's your ratio. Does it make sense? If someone say that okay, you want to keep that door open, then you need to sum that door as well. D4 is 1 times 2.2. If someone said I also want to keep this D3 open along with this one, then you will say okay, you need to plus another one as well, 3.6 by 4, right? So you sum all the remaining one down, the one opening that you want to consider is on the top. Does it answer your question? So do you understand that? So that's where are we now? Okay, 28 over 1.56, so you will get 18.5, which is, you come back here on these tables. So you come back here, then area of opening 6 or more. So in that case, we need to use this row, and our largest opening on windward walls. Yes, we have largest opening on windward wall. So you need to take CPI equal to CPE for windward wall. You got the point? So CPI is equal to CPE is equal to 0.7, because this is the windward wall, right? Because the opening on windward wall, so you need to take the largest opening on windward wall. So CPI equal to CPE. CPE of windward wall, we know 0.7, positive 0.7. So if you take the positive 0.7, and this is applied everywhere, and the positive values, how are you going to take it? Positive values, I think there is a pressure sign, that positive values that you're going to take it is this one. This one is positive when it goes, when you inflate the structures, right? It's try to inflate the structures, and that will also verify that one. So you have a 0.7 here, 0.7 here, 0.7 here, CPI, and that's validated, right? You can physically see that when the wind is blowing from here and you keep this door open, your structures will try to inflate, right? It will try to inflate that one. So that sounds good. 0.7 makes sense. And if you have 0.7, then internal pressures that you're going to, okay, combination factors that we're going to take it. Let me take you through that combination factors, because these combination factors comes here as well. So here, for these combination factors, for simplicity, I think we just want to take the one. We don't want to make it there is anything combined with this one, like internal pressures. We did not consider any combination factors. So in this case, we are not combining any surfaces. Let's say one effective surface. So you have one here. So KCI equal to 1. Now for that case, let's say same like here, 0.96 internal pressures is equal to 0.96. CPE is 0.7, and then you have 6 meters. Then if you work it out, that internal pressures would be 4 kilonewton per meters, right? So if I draw it up here, the internal pressures that you're going to get, the UDL load on the frame would be 4 kilonewton per meters. Let's say this is case number 3, coming from internal pressures. Someone might say that, okay, let's keep the, someone might say, okay, someone might say that let's keep the D1 and D2 close and let's open D3 and D5. Let's open here. So I think the story will be still the same. We need to calculate the pressure, internal pressure in that case. The internal pressures Pi equal to 0.96 C fig I and C fig I equal to CPI KCI. Now in that case, now wind is, again we need to calculate the ratio, right? Because we have only two tables for CPI. This one completely closed, no opening. Here we keep the door open. So we again need to calculate the open area ratio. So for that case, let's do the opening ratio here again. The opening business. The opening business is this will stay the same. This 1.56. This door D3. The area of door D3 is 3.6, 4.5. 3.64. So that is D3. So that is 3.6 times 4. You get 14.4 meters square. And you have D5 open. D5 is 1 times 2.2. That is 2.2 meters square. So 14.4 plus 2.2, you have 16.6 meters square. So the top one is 16.6 meters square opening, or the remaining opening on the other surface is 1.56 meters square, right? The air vents. So you will get this ratio of, you get 10.6 ratio. So again it's 10.6. So in that case you have 10.6, which is greater than 6. This ratio is greater than 6. Now the area opening is on windward wall now, right? Because you have area of opening on windward wall. It's not leeward walls, because you can see that wind is coming from here. So this is the leeward wall. So the leeward wall is open. So in that case, CPI equal to CPE of windward wall. So in that case, CPI is equal to CPE of windward wall. Now CPE of windward wall, you can go back here, and I think you know the CPE of windward wall, we calculated that one. That is minus 0.5, right? If you remember that on our previous video, we done these, and we have minus 0.5 this case. So we have minus 0.5, minus meaning it's going to deflate your structures. Minus 0.5.
Are you looking at windward or leeward wall?
Yes, so where is the opening? Let me ask you the questions. Okay, so we will have a opening on leeward wall. So we consider CPI of leeward wall, and the CPI of leeward wall equal to CPE of leeward wall, and then we consider leeward wall. Okay, does it answer? Is it okay? So you have, yep, you have minus, and KC is 1. So you have this 0.96 times 0.5. Don't worry about the sign. We will put the arrow for that. And you have 6 meters portal frame distance. You get 2.9 kilonewton per meter. So if I draw the portal frame now, that you have this UDL load coming on to this portal frame, which try to pull it, that is 2.9 kilonewton per meter. That is case number 4, that is internal pressures. Now we can combine those. We will combine those load cases. Let's say wind load case number 1. Let's combine case 1 plus case number 3. Case 1 meaning this is external pressure, plus you wanna keep the door on windward wall. Right, so that is case number 1. So let's say case number 1 is 1 and 3. So for here you have arrow going here. Please note the arrow will be the important here when you combining. This is case number 1, by the way. Yeah, this is case number 1. So you have 4 going pushing the wall, and case number 3 you have 4 going in the opposite directions, right? So 4 is going here and 4 is going in this direction. So you have 0 force, stabilize that. So there is no any force on the windward walls. So there is 0 force. Now we will check the next one, roof. Case number 1. The roof is 4.1 going in this directions and going up, and you have 4 is also going in this direction. So 4 plus 4.1 you will get 8.1, and you have this first one, you have 8.1 kilonewton per meters, right? I hope you understand these combinations. Now you have 2.3 and the pressure is 4, so 6.3. So all the way to here is 6.3. Let's put for completeness is 0 here and 6.3 here. And then case number 1.4 is pulling, and from inside is also 4 pushing that way. So that will give you 5.4. So that's both are going here, which is 5.4 kilonewton per meter. That is kilonewton per meter. And here you will have a 4 going in this direction and 2.9 going. So 4 and 2.9, 6.9. So you have a 6.9 blue because it's 6.9 kilonewton per meter. I hope you understand that. So this is wind load case 1, and let's say wind load case number 2, that you're going to combine 1 and you're going to combine 4, right? So keep the 1 external pressures and we're going to combine with 4, right? That is the door opening on leeward wall. So we will have a 1 which is 4 going in this directions, and this is 2.9 going on this direction as well. So 4 and 2.9 is 6.9. So you have this one rate 6.9 kilonewton per meter. Then you have this 4.1 because this is case number 1, 4.1, and you have 2.9. So 4.1 take away 2.9 because 4.1 is going this way and 2.9 is inside coming here. So 4.1 take away 2.9, you will get, let me check what was that again. You have case number 1, 4.1 take away 4.1, and then you have take away 2.9. So 4.1 take away 2.9, you get 1.2. So you get 1.2 in which directions? Because this 4.1 is more here on this direction, so that is 1.2 kilonewton per meter. Similarly, you can have this one. So you have a 2.9 and 2.3, but 2.9 is more, but we need to take away. So you have 0.6 going down. By the way, this is red, is 0. How much was that? 0.6. And similarly, I hope you understand the story now, that you can take it 1.5 and also you have a 0 here. Right, so I hope you understand this one, the combination of 2, 1. Now let me talk you through this